Okay, let me go here. So chapter 12 is what we're going to discuss. And in chapter 12, the focus is on bonding, all right? Again, I'm assuming that you watch the videos. And if you did, you would realize that bonding is basically, in chemistry, when we're talking about bonding, we're talking about a force, which basically holds atoms in the case of molecular compounds and ions in the case of ionic compounds together, right? So that they don't fly off and separate from each other spontaneously, right? So basically what this chapter is dealing with is an examination of the different forces that are at work when it comes to these compounds being held together, all right? Now, the first thing I want to talk about here is the concept of electronegativity. So let me get myself together. Let me get myself together here. So electronegativity is basically a term that is used to describe the attraction that atoms will have for electrons that they're sharing with other atoms. So to put it into words right here, electronegativity is the ability of an atom to attract shared electrons, all right? So that's what electronegativity is, right? So if you have two atoms bonded to each other, they will share electrons to different extent if the atoms are different. If the atoms are identical, then basically they will share the electrons evenly, right? If you have a situation where you have one atom is more electronegative than the other atom and they're bonded to each other, the one that is more electronegative will basically have a greater attraction for the shared electrons, right? So therefore, those shared electrons will, on average, be closer to one atom, the more electronegative atom, than the other. And there's a guy by the name of Linus Pauling. He came up with a scale, a 4-point scale, to quantify electronegativity. And I'm going to go to the tables document that you'll have access to. And I think it's on the very last page. So let me click here. And let me download this. Oh, wait a minute. It's not downloaded yet. Okay. And it's the very last page right here, right? So this here is a table which Linus Pauling came up with. If you look in different textbooks, you'll see different variations, especially with the numbers. But for all purposes, we'll be using the numbers provided here, right? So basically, he came up with this scale based on several quantitative factors, including thermodynamic data. And based on his scale, you have this table right here, which has these electronegativity values. Based on his scale, the highest possible electronegativity value would be 4.0, which is fluorine. So fluorine is the most electronegative element in the periodic table, right? And there are certain trends that we can observe with respect to the periodic table and electronegativity values. What you'll find is that generally speaking, there may be some exceptions, but generally speaking, as you go from one element to the next across a period, left to right, the electronegativity value would increase, all right? So if you look at, for example, period 2, which starts with lithium, you'll see that it starts off with lithium at 1.0, then 1.5, and then it increases up to 4.0 in the case of fluorine. And that's a general trend. There are some exceptions, but generally speaking, that's what you observe going from left to right, all right? And then going from top to bottom of any group, what you'd find is that the electronegativity value decreases. Again, there are some exceptions, but that's a general trend. So if you take, for example, make sure you get one of those. If you take, for example, group 1A, scroll in here, oops, sorry. You'll see in the case of group 1A that the electronegativity values decreases from 2.1 in the case of hydrogen to 1.0 in the case of lithium, and then it goes down to 0.7 in the case of francium. So that's what you'll observe, generally speaking, going down any group. Again, there are some exceptions, but that's a general trend, all right? So we can use these values to determine the nature of the bond that exists between any two atoms in the periodic table. And there is, again, you'll see different textbooks having variations of what I'm about to say, but basically there are different criteria that we use to determine the type of bond that is involved based on these values. So what I'm going to do is I'm going to open this up here, and I'm going to construct a little table, which basically summarizes the criteria, right? So it's a very small table where here I'm going to have the different, I'm going to have the difference in the electronegativity values, and here I'm going to have bond type, all right? So if the difference in electronegativity values vary between 0.0 to 0.4, then the bond type, for all intents and purposes, well, not all, for most intents and purposes, we classify this bond as nonpolar covalent. And what that means is that the bond is basically one where the electrons are shared evenly, right? So if you subtract or find the difference between the electronegativity values between two atoms, and if that difference fall within that range, 0.0 to 0.4, then we say that that bond is, for most intents and purposes, nonpolar covalent, all right? Now, if the difference goes from 0.5 to 1.7, it's 1.7, then for most intents and purposes, that bond is considered to be polar covalent, all right? And what that means is that there's a significant difference in the electronegativity, so much so that the electrons shared between the atoms will be attracted to one atom compared to the other, all right? So that's basically the case where the difference in the electronegativity value is ranging from 0.5 to 1.7. And then if you have a difference in electronegativity values going from 1.8 to greater, right? So whatever number above 1.8, then that bond, for most intents and purposes, is considered to be ionic. And what that means basically is that if the difference in electronegativity is that great, 1.8 or greater, then you have the complete transfer of electrons from one atom, which would be the less electronegative atom, to the other atom, which would be the more electronegative atom, right? So this is basically the criteria that we're going to use. As I said before, in different textbooks, you're going to see, a wide variety of, criteria that is used to establish the type of bond that connects two atoms. In this case, we're just using what I just showed you here, all right? So that brings us now to the first question in the assignment. So let me go to here, right? Because this question is asking for you to determine the type of bond that will form between each pair of atoms in the table. And it says you're going to use the electronegativity chart and the bond type chart to help you. So basically what I just showed you is what you're going to use, right? Now, I wish I could have done a split screen here, but hold on, let me take this out here. Oh, by the way, I should check to see if I have published the assignment for you guys out there in Zoom. Let me just do a quick check here. Okay, so let me publish that now for you guys out there in Zoom. Okay, so you guys out there in Zoom should now be able to access assignment number 12, all right? So this is assignment number 12, and this is the table that you're going to use. So let me take this out and put it aside so we can refer to it. Okay, and this is the assignment here. Take that aside, put it over here. Okay, so the first pair of atoms is arsenic and sulfur, right? So the first thing we need to do is calculate the electronegativity difference between sulfur and arsenic. So sulfur is 2.5. So let me okay. So sulfur is 2.5 and arsenic is, what's arsenic? 2.0. All right. So 2.5 minus 2.0 gives you 0.5. All right. So 0.5, if you remember the short table I drew up, 0.5 would put the bond type in the category of polar covalent. Or let me just put PC. You can just put PC because that's the option that they give you. So the bond is polar covalent because 0.5, for polar covalent bonds, the difference in electronegativity would be from 0.5 to 1.7, right? So that's basically how we answer that, all right? For the next one, is cobalt and bromine, right? So we have to go to the periodic table, or not the periodic table, the electronegativity table, and we see 1.8 for cobalt. So let me write this down here. 1.8 for cobalt minus for bromine. What's the value for bromine? For bromine, the value is 2.8, right? So 1.8 minus 2.8 gives you, no, cobalt, okay, right, 1.8 minus 2.8, and you use the absolute value, right? So that would be 1.0. 1.0 would put that also in the category of polar covalent. Again, because polar covalent bonds are the bonds where the atoms have a difference in electronegativity going from 0.5 to 1.7. So 1.0 falls within that range, all right? So what I want you guys to do right now is to complete the rest of the table, all right? Right now, I want you to basically do like what I just did. First, find the difference in the electronegativity values, and then based on the difference, tell whether or not the bond that is formed between these atoms fall into the category of either non-polar covalent, polar covalent, or ionic. So what I'm going to do is clear the screen. And to help you, if you don't have the table itself, I'm going to leave the table up here for you to use to answer, to complete that table. All right? So I want you to do that now because I want us to complete that and move on to some other stuff. And let me know when you're finished so that we can move on. Okay, so let me see. Miss De La Vega is saying, what? Zoom appears frozen. I don't think it's frozen. I just left the screen up. I mean, the tables up on the screen because I figured you guys are going to need those values to do the question one from the assignment. Oh, okay. Yeah, just let me know when you guys are finished with that question. Okay, are we almost finished? All right, let me give you 2 more minutes and then we'll move to the next topic.
Sir.
Yes, sir.
For the first one, you did a 2.5 minus 2.0, and then
I'm sorry, repeat that?
like for the first one,
Uh-huh.
arsenic and sulfur, you did 2.5 minus 2.0, and then for the next one, you did 1.8.
Hold on, I can't hardly hear you. You said what? For the first one?
You did 2.5 minus 2.0, and then for the second one, you did 1.8 minus 2.8. It doesn't matter which one we put first.
No, as long as you write down in the answer the absolute value. It's an absolute value, which is the difference between those two. That's what you're going to record. Yeah. Okay, let's proceed to discussing the other topics for the next question. And this has to do with Lewis structures. All right. So let me just say a few words about that. Let me go back to this again and let me delete this here. Okay, so Lewis structures basically is a way of representing molecules or polyatomic ions, all right? And basically these structures are used to show how the atoms are connected to each other, and gives you some additional information as well, in terms of the type of bonding situation, whether or not it's shared electrons, and whether or not the electrons that are shared are bonding, and then you have some other electrons that are known as non-bonding. I'm going to get into all of that in this discussion. So I'm just going to go directly into one example. So the first example I'm going to get into is, let's say you're given a molecular formula of CH4. Oops. So let's say you're given the molecular formula CH4, right? And you're asked to draw the Lewis structure of this molecule. So the first step in this process would be to go to the periodic table and you look up the group number, because the group number gives you the number of valence electrons. The valence electrons are those electrons that are on the outermost shell, right? So in the case of carbon, if you go to the periodic table, you see that carbon has a valence electron shell number or group number of 4, right? And then in the case of fluorine, there are 7 electrons, or the group number is 7, which means that it has 7 valence electrons. But because you have a 4 here, you have to multiply that by 4 to give you the total count, which will be 28 electrons contributed by the fluorine. So the next step is that you would add the 28 to the 4, and that gives you 32 electrons. And what I like to do is that I like to express this as the number of electron pairs. So that will be 16 pairs of electrons, all right? So the next step is that we identify the element that is the less electronegative element between these two. So if you go to the previous table I showed you, you'll see that carbon is of a lower electronegativity value compared to fluorine. So you're going to put the carbon in the middle and surround it with the fluorines, like this, right? And then the next step is that you put the bonding pairs first between the carbon and the fluorines. Now remember, you have 16 pairs to assign, all right? So of the 16 pairs, I'm going to put the first pair here, and this line here represents a pair of electrons, by the way, right? So this represents an electron pair. In fact, this represents a bonding pair. Let me write that down. Bonding pair of electrons, all right? So we put one line here, that's one pair, second pair goes here, third pair goes here, fourth pair goes there, all right? So what we have done so far is assign 4 of the 16 pairs that we have to play with. So the question now becomes, where will the other pairs go? And the answer is that the other pair or pairs will end up on the fluorine atoms, right? So those pairs are called non-bonding pairs because they are not shared between the fluorine and the carbon. However, you have to be careful. You have to make sure that when you assign the pairs on the fluorine, you do so that each fluorine ends up with an octet or 8 electrons on the outer shell, right? So in the case of this fluorine, it has 1 pair already. So I would put 3 pairs here, 1, 2, 3, right? So that would be 8 pairs of electrons around the fluorine. Here, 1, 2, 3, that's 8 pairs. Again, 1, 2, 3, and then 1, 2, 3. And that would basically be the Lewis structure for carbon tetrafluoride. you have 4 pairs that are bonding, and then you have a total of 12 pairs, 3 each around each fluorine atom, which will be non-bonding, and that adds up to the total of 16 pairs that we have to assign. And therefore, this would be the Lewis structure. So I identified the bonding pair here. The non-bonding pair would be the pair of electrons not involved or not shared between any of the 2 atoms. So non-bonding pairs. In some textbooks, they call them the lone pairs. Same difference. All right. So that's basically it as far as the Lewis structure for carbon tetrafluoride is concerned. And those are the steps that you'd have to go through in order to determine the Lewis structure of pretty much any molecule or any ion. All right. Any questions about this example? Any questions? Any questions? Any questions out there in Zoom? Oops. Or something went wrong with the Zoom. Okay. It seems as if there are some connectivity issues with the Zoom, but I think you guys are back on, at least on my laptop here. So let me share my screen. Hold on, what's going on here? For some reason, oh, here it is, okay. Okay, so I don't know, what you guys out there have missed, but I just went through an example of determining the Lewis structure of CH4. So if there's anything that you need explaining, please feel free to stop me and I can go back and discuss whatever I need to discuss, all right? Okay, so let me just move on to the next example. Let me clear this here. Okay, the next example I'm going to use is, let's say you're given this formula, SCl2. So this is the formula of sulfur dichloride. SCl2, all right? So the first step, as in the previous example, we will consult the periodic table to look up the group numbers, right? So in the case of sulfur, the group number is 6. In the case of chlorine, the group number is 7, but because there are 2 of them, I have to multiply that by 2, right? So that gives you 14, which means that the grand total of valence electrons in this molecule would be 20 electrons, which would be equal to 10 pairs. All right? Then I'll put the sulfur in the middle. Again, the atom that goes in the middle would be the one that is the least or less electronegative. So the sulfur would go in the middle, and we surround it with the chlorines, right? And I already put in the bonding pairs here. Remember now we have 10 pairs to play with. So we put 1 pair here, 1 pair here, and then 3, 4, 5, 6, 7, 8. So we have used up 8 of the 10 pairs. So the next question is, where would the other 2 pairs end up with? And the answer is simple. It will go simply on the sulfur atom. And if you look at this molecule carefully, you'll see that each atom ends up with 8 electrons, octet, right? So this chlorine here has 2, 4, 6, 8 electrons. The same is true for this chlorine. And the sulfur here has 2, 4, 6, 8 electrons. That's it, all right? And that's basically how you do that molecule, all right? Any questions about this one? Any questions? Any questions? Okay, let's move on to another example. Let's say you're given SiH4. All right. Now, in this case here, silicon is in group 4, so it will contribute 4 electrons. Hydrogen is in group 1, but there are 4 of them, so therefore we multiply by 4. And then this adds up to give you 8 electrons, which will be equal to 4 pairs. All right. So I'll put the silicon in the middle, surrounded with the hydrogens. Now, in this case here, what I would do is put the bonding pairs. We have 4 pairs to play with. 1, 2, 3, 4. And that's it. We have used up all 4 pairs, and therefore this would be the Lewis structure for silicon tetrahydride. All right? Any questions? Okay, let me give you another one. Let's say, okay. So let's say you're given H2SE. Now in this case, if you were to look up the values, let's see what the values are in terms of the electronegativities. Hydrogen is 2.1 and selenium is 2.4, right? Now you might be tempted to put hydrogen in the middle and selenium not in the middle, all right? However, we cannot do that, even though hydrogen has a lower value. And the reason why, if I can go back to this right here, is that hydrogen can only have 2 electrons on its outer shell, right? So hydrogen is considered to be what we call a terminal atom. In other words, you cannot have hydrogen simultaneously bonded to 2 other atoms, all right? So in this particular case, the selenium would be in the middle, and we surround it with the hydrogens, right? You will never have hydrogen in the middle of a structure because, as I said before, hydrogen cannot have more than 2 electrons on its outer shell. So what we do first, in fact, I should have done this first, we count up the valence electrons. So for hydrogen, that would be 1 times 2, which would be equal to 2. And for selenium, that would be, selenium is in group 6, so therefore that's 6. So therefore 6 plus 2 gives you 8 electrons, which would be equal to 4 pairs. And then we start assigning the electrons. This is the arrangement here. We put the bonding pairs first, 1, 2. So we have 2 pairs to assign. Now the question is, where will those pairs go? Well, those pairs cannot go on the hydrogens because of what I said earlier. Hydrogen cannot have more than 2 electrons on its outer shell. So this hydrogen already has 2, this hydrogen already has 2. So that means that the remaining 2 pairs of electrons will go here and here. And therefore this would be the Lewis structure for hydrogen selenide. All right? So that's basically how that is done. So the reason I'm going through these examples so that you know how to tackle these problems so that we can do the problems that is given in this assignment. Okay, any questions about this one? Any questions? Okay, let's try another one. Suppose you're given NBR3. Let me hear what you have to say about this one. Oh, what's the first step in this process based on what we have done before? And you guys out there in Zoom, please feel free to chime in. What's the first step in this process based on what we have done so far? Okay, so we count the number of valence electrons. So, whoops. So, what's the number of valence electrons that nitrogen will contribute? You have to go to the periodic table and look for the group number, right? Which is what? 5. Okay, very good. What about bromine? What's the group number for bromine? 7, exactly. But because we have 3 here, we have to multiply that by 3, right? So that gives you 21 from bromine. When you add these up, you get a total of 26 electrons, which would be equal to 13 pairs, all right? What's the next step?
The middle.
Okay, and I can understand the reason why I say that, but again, this is one of those situations, somebody's saying something in the chat. Hold on, let me see here. Okay, somebody's asking, where do you find the valence electrons in the periodic table? And the answer is, it's a group number. So whatever the group number is, that would be the number of valence electrons. Now, let me just say this. That is only true for the elements that are called the representative elements, which are the elements in the A region of the periodic table. So that's not including the transition elements, right? So we won't be doing any problems where you're asked to determine the Lewis structure where there is a transition element involved, all right? But to answer your question, and this question is asked by Miss Patterson, to answer your question, the answer is that you look for the group number. So nitrogen is in group 5, so that will contribute 5 valence electrons, and bromine will contribute 7 each, because bromine is in group 7, all right? Now, going back to what you were saying that bromine would be in the middle. Yes, I would probably be tempted to think that. However, because you have 3 bromine atoms here, it is more likely that nitrogen would be in the middle, all right? So what I would do is start off with the nitrogen, and somebody's asking another question. Let me see. Let me see what this person is asking. Oh, she's just thanking me, all right. So nitrogen is in the middle, and then we surround it with the bromines, right? And then we start off with the bonding pairs. Now remember, we have 13 pairs to assign. So 1, 2, 3, all right? Then we put in the non-bonding pairs around the bromines, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we have used up 12 of the 13. So where will the 13th pair of electron go? On the nitrogen. And that would be the Lewis structure of nitrogen tribromide. So this is one of those situations where, again, even though in most cases the least electronegative element will go in the middle, but in this case here, because you have 1 nitrogen and 3 bromines, I would put the nitrogen in the middle and surround it with the bromines. All right? Okay. Any questions about this one? Any questions? Okay. Now, what I'm going to do is do some examples of polyatomic ions. Let me clear this here. And which one shall I do? Let's see. Suppose you're given the chloride ion, which is ClO2 minus. Hold on, will this work? Okay. So we go through the steps before, but we have to make a slight modification because of the negative charge. So let me explain how that works. So the chlorine, you go to the periodic table, you look up the atomic number, the group number of chlorine, and that will be 7. And then you do the same thing for oxygen, that will be 6, but we multiply that by 2, so that will be 12, right? Because of the negative charge here, what that means is that we need to add an extra electron, right? So for every negative charge in an ion, you add an electron to the total valence electron count, right? And you're going to see later on, I'm going to do an example with a polyatomic cation. For every plus charge that is present, you subtract an electron from the total electron count, valence electron count, right? In this case, you add an electron because of the negative charge. So that's 7 plus 12, 19 plus 1, 20 electrons, which will equal to 10 pairs, all right? So we start off with the chlorine, put the oxygens around it, and then we put the bonding pairs, 1, 2, then 3, 4, 5, 6, 7, 8, and then 9, 10. All right? And that's basically it, excepting that you have to finish this off by putting the structure within square parentheses and then put a negative sign out there to indicate that the entire structure carries a negative charge. And that's it. That's how you would deal with this particular situation. All right? Any questions about this one? Any questions? Any questions? All right. Any questions out there in Zoom? Any questions? All right. Let me clear this. I'm trying to think of another example. That would be a good one before we get to the actual questions in your assignment. Suppose you're given Man, I'm not good at creating questions, I must admit. Okay, here's one. Suppose you're given CH2O, which by the way is a compound known as formaldehyde that is used by those guys who operate funeral homes to preserve human bodies for funerals and so on. Anyway, so let's say you're given this and you're asked to draw the Lewis structure. So we go through the steps as before. Carbon will contribute 4. Hydrogen will contribute 1 each, and there are 2 of them, so we multiply that by 2. And oxygen will contribute 6. So that would give you a total of what? 4 plus 2, 6 plus 6, 12 electrons, which would equal to 6 pairs, all right? So we put the carbon in the middle, and this time we surround it with the 2 hydrogens and the 1 oxygen, right? So after that, we put the bonding pairs, 1, 2, 3, and then we put the non-bonding pairs, right? So we cannot put the non-bonding pairs around this hydrogen, nor this hydrogen. That means that they can only go around the oxygen. So that's 4, 5, 6, all right? Now, this is not going to be the final answer. And the reason why is because, remember, we're trying to have each atom ending up with 8 electrons on their outer shell, right? Now, that is true for oxygen. In the case of hydrogen, they cannot have 8. They can have a maximum of 2, right? So that's fine for the hydrogens as it is right now, here and here. But carbon has 2, 4, 6 electrons on its outer shell, right? So therefore, it needs another pair of electrons. And it can get that other pair of electrons because this pair of electrons here from the oxygen can come here to form an extra bond. And therefore, the final answer is going to be this, H, C, H, double bond O, and then you have 2 lone pairs here. So now each atom is now satisfied in terms of the maximum number of electrons that their outer shell can accommodate, including carbon, because as you can see here, the carbon will have 2, 4, 6, 8 electrons. Oxygen still has 8 electrons, and the hydrogen, of course, will have their 2, which they're satisfied with. So therefore, this would be the final answer right here. All right? Okay, any questions about this? Any questions? All right. Now, there's one other thing I need to talk about because the question that is asked in your assignment, you're asked to give the Lewis structure and the geometry. Let me as quickly as I can, talk about that. Now, there's a chart which I've decided I'm going to make available to you, which basically gives you the shapes of different molecules based on their Lewis structures. Because the thing about the Lewis structures is that the Lewis structures is only, what's the word I'm looking for? It gives you only information about how the atoms are connected to each other. It doesn't say anything about the actual 3-dimensional shapes. And 3-dimensional shapes are very important, especially when it comes to understanding certain properties that compounds have. A lot of it has to do with the shape of the molecule, all right? Now, there is a chart. Let me see if I can bring this up here. Let me minimize this here. Get rid of that. Go to files. And let me back up to here. And where is it? Oh, let me go tables. Okay, so this is the chart right here. I'm downloading right now. Okay, so this is a chart here that you're going to use to help you to predict the shapes of molecules. And for all purposes, what I'm going to do is I'm only going to focus for all purposes on this region right here that I'm circling. So we won't be dealing with molecules where all these here would apply. Okay, somebody's asking a question here. Since there are 3 elements, I thought you divide by 3 instead of 2. Okay, I'm not sure what you're referring to, Ms. Patterson. Let me see here. Are you talking about this molecule, this example that we just did? Okay, so you're saying that because since there are 3 elements, I thought you divide by 3 instead of 2. I'm still not sure what you're referring to. There are 3 elements here, carbon, hydrogen, and oxygen, right? What I did was that I write down the valence electrons, which you can get from the periodic table, the group number. Carbon contributes 4, hydrogens contribute a total of 2, and oxygen contributes a total of, oh, I think I know what you're referring to. You're talking about going from here to here. Yes, okay, so basically what I did was that I divide by 2 because I want to express the amount of electrons in terms of pairs. Right, you always divide by 2 to go from the number of electrons to pairs. So that's why I divide by 2, all right? Okay, I'm glad I can answer your question. All right, so let me go back to what I was talking about here, right? So this is a chart that you're going to use to basically predict the shape and the bond angles for different molecules based on your Lewis structures. So let me just briefly try to describe what's happening here. So let's say you have an atom, let's say you have a molecule where you have an atom bonded to 2 other atoms in this way, right? So you have bonding pairs here, no lone pairs on the central atom. Then the shape of that molecule will be linear. In other words, you can draw a literal straight line from one atom, X, through the central atom to the other atom, right? So basically, any molecule where you have 2 bonds like this, and no lone pairs, then that shape would be linear. Now, if you have, on the other hand, an atom like E bonded to 3 other atoms, right? So basically, there are 3 bonds, then the shape of that molecule would be trigonal planar, right? And the bond angle here would be 120 degrees. Now, if instead of this atom here, you have a lone pair. So here you had a bonding pair, but now you have a lone pair. In terms of how the electrons are arranged, the geometry will be trigonal planar, but the shape is determined by the positions of the atoms. So therefore, as you can see here, it's a bend shape from X to E to X right here. So the shape of this molecule would be bent or angular, and the bond angle here would be approximately 120. Actually, it's going to be less than 120, but approximately 120, all right? And then now, if we have a situation where the central atom is bonded to 4 other atoms, then the shape adopted would be tetrahedral, right? Where the bond angle here would be 109. Now, if one of these atoms is removed and you're left with a lone pair here, you're going to have this shape here where the shape of the molecule determined by the atoms would be trigonal pyramidal, all right? And then if you have another atom removed and you have a lone pair here, then the shape would be bent or angular, right? But please note that this bent shape here would have a different bond angle compared to this bent shape right here. This bent shape, the bond angle will be 120. Here is going to be 109, all right? And that's pretty much what you need to be concerned with when it comes to the shapes of the molecules. The others below at this level, you don't need to be concerned with. For those of you who have to do general chemistry 1, you're going to be dealing with those, but not for our purposes. So if I were to apply this idea, let me see if I can minimize this here. If I were to apply this to the previous question example that we did, let me move this down. Hold on, let me do this. Okay, let me minimize this. Okay, so let's say you're asked for the shape of the formaldehyde molecule that we just worked out here, right? So this is the formaldehyde molecule, right? We have the central atom here bonded to 2 hydrogen atoms and an oxygen, right? So what I would do is look at this table to see which of these shapes matches up with what we have here in the case of formaldehyde. If you have a central atom bonded to 3 other atoms, that looks like this particular arrangement. I'm sorry. That looks like this arrangement right here, where you have the central atom. No, I'm sorry, this arrangement, my bad. This arrangement right here, where you have the central atom bonded to 3 other atoms. It's the same thing as this, the carbon atom bonded to 3 other atoms. And please note, it doesn't make a difference if one of the bonds is a single bond, double bond, or triple bond. That does make a difference, right? So even though you have single bonds indicated in this structure here, you have a double bond here, you treat it like a single bond for the purposes of determining the shape of the molecule. So basically, since this here parallels this in terms of the spatial arrangement, that means that the shape of this molecule would be trigonal pyramidal or pyramid. And that's basically how you're going to determine the shape of the molecule based on the Lewis structure. All right? So with all that said, let's get to the actual assignment. So let me clear this here to avoid confusion. And let me get rid of this. And let me get to, okay, what is this here? Oh, that's a previous assignment. Where did this come from? Okay. All right, so let's scroll down to this problem right here. So we go through the steps as before. In this case, I would put the chlorine in the middle. No, hold on. Which one is the least electronegative? Let me see. You could put the nitrogen in the middle. That's, but I think chlorine is more electronegative, or is less electronegative. Or chlorine is 3, nitrogen is 3, so it doesn't matter which one you put in the middle. And fluorine is 4. So I would put nitrogen. You could put chlorine. I wouldn't penalize you for that. But I'll put nitrogen in the middle. But first, let's do the valence electron count. So nitrogen will contribute 5, oxygen will contribute 6, chlorine will contribute 7. So that's 5 plus 6, 11 plus 7, 18 electrons, which would be equal to 9 pairs, all right? So I'll put the nitrogen in the middle, chlorine and oxygen on either side, and then I'll put the bonding pairs first. 1, 2, then 3, 4, 5, 6, 7, 8, 9, all right? Now, the next step is that you recognize that nitrogen does not have 8 electrons. So what I would do is push these pairs of electrons here. You could just as well put the pair of electrons from the chlorine here. Again, I won't penalize you for doing that either, but I'm just going to put the pair of electrons here for the oxygen to form a double bond with the nitrogen, and therefore the resulting structure would be double bond O with 2 lone pairs, and then Cl with 3 lone pairs, all right? Okay, so this would be the Lewis structure. So we would have answered that part of the question, but the next part of the question has to do with the shapes. So basically, we have to use the chart that I showed you earlier. Let me see if I can bring that chart up. Okay, so let me put, where should I put this so that it doesn't, okay. All right. So remember now, we're only concerned with, for all purposes, this part right here. All right? Okay, so my question to you is this. Which one of these structures here in the chart would best fit what we have here in the Lewis structure of the molecule that we just determined? Now remember, in this structure here, we have a central atom bonded to 2 other atoms and a lone pair, right? So which of these structures, and I think somebody's answering that question. Okay, somebody says linear. That would be incorrect. Can anybody tell me why that's incorrect? Exactly. In the case of the linear structure, there's no lone pair on the central atom. So you have to look for the one that has two bonds, right? And a lone pair on the nitrogen, on the central atom. So which one of these would fit that description? Okay, let me see. Somebody else is saying something. Okay, so yep, that's correct. Somebody says bent, and that is indeed correct, because that would fit this one right here, right? So the answer is bent. And even though the question is not asked, if you were asked what would be the bond angle, you would say approximately 120 degrees, because that's what this says right here. All right? So that's basically how you would determine the shape of the molecule. So as I said before, you'll have access to that chart. So in your test, make sure that you say to your proctor that you expect that chart to be there as well. All right? Any questions about this one? Any questions? Any questions? Okay, let's see if you can do the other one. Okay, let me clear all this here. And let me do this. I want to keep this chart up here. So let me, okay, let's look at this one. COCl2. So what's the first step? What's the first step? COCl2. And again, you guys out there in Zoom, please feel free to chip in with your answers. What's the first step? How many electrons does carbon contribute? Okay, somebody's answering over in Zoom. 4, okay. And what about oxygen? Okay, oxygen would be 6, and chlorine would be 14, 2 times 7, 14. Okay, very good. So when we add this up, you're going to get a total of 24 electrons, which will be equal to 12 pairs. All right? So what's the next step? What's the next step? Now that we have the total valence electron pair count, with the carbon in the middle and surrounded with the oxygen and 2 chlorines. All right? And then the next step is?
Draw the bonds.
Bonding pairs first, right? So remember now, 12 pairs would be the total number of valence electrons. So we're going to put 1 pair here, 2 pairs, 3 pairs, all right? Then 4, 5, 6, 7, 8, 9, 10, 11, 12. What's the next step?
When the oxygen's lines, like with the carbon, so it's like a
You
double.
mean like doing this?
Yeah.
And that forms a double bond here because carbon has 6 electrons, it needs 2 more, right? So therefore the final answer in terms of the Lewis structure would be C double bond O, lone pair here. Chlorine will have 3 lone pairs here, and the same will be true for this chlorine here. Okay, so the next question is, so let me bring up the chart. Is what, oh, sorry, you had a question?
No matter which side you put the line on for the oxygen, because you see how it used to have like 3 of it around it, and you move the one from the left down.
No, it doesn't matter, no. No, it doesn't matter. Okay, so let me pull up the chart now, because this is what you're going to use to tell the shape. So which one of these structures, and remember again, let me circle the region that we're concerned with. We're only concerned with, at our level, this right here. right? So which one of those would this molecule fit?
The triangle.
The trigonal, trigonal what?
Triangle here.
You sure about that? Trigonal pyramidal? I don't think so. Central atom bonded to 3 other atoms, no lone pairs.
Oh, is it tetrahedral?
No, tetrahedral have 4.
Trigonal planar?
Exactly, trigonal planar. Because in the case of trigonal planar, you have the central atom bonded to 3 other atoms. That's basically what we have here, the central atom bonded to 3 other atoms, right? So that would be the shape of the molecule. And just for the sake of it, what would be the bond angle? What would be the bond angle? Even though that's not the question being asked, but I'm just asking, because it could be asked that question in the test. What would be the bond angle? 120 degrees would be correct, and that is said by Oliver and Jablonski. Please forgive me for mispronouncing your name. All right, so that's basically how you would do these questions. So what I'm going to do is, hold on, let me do this here. Let me clear this here. Okay, so basically what I'm going to do is leave the rest of these for you to do, right? We have just done the first 2. You should be able to do the others based on what we have described, based on the examples that we have looked at before, all right? Okay, with that said, your next test will be next week, right? And that test, I'm going to send it to the testing center over the weekend. And as soon as I do that, I'm going to post an announcement, again, giving you details about what the test should look like, you know, what the front page should look like and how many pages. So that, again, even though some confusion have happened in the past, but hopefully they'll get it right this time, right? This test will be based on chapters 7, 8, and 9, because test 1 was 1, 2, 3, test 2 was 4, 5, 6, test 3 would be 7, 8, 9, right? I'm in the middle of grading assignment 9 right now, right? So I'm hoping to get that sent to you by this evening. What I'm going to do in the meantime is publish the answer key for assignment 9, so you have at least that to study off of, all right? So make sure you sign up, you know, in the testing center schedule. Make sure you get a slot for next week. And if there are any issues with that, then you probably can come to my office during office hours and do the test during that time. But I prefer that you try to get at least a slot for your test, all right? So that's the first thing I want to say by way of announcement. The next thing I want to talk about is for next class, I'm going to publish the modules for chapter oh, wait a minute, hold on.
Sir.
Yes, sir.
And the final is May 5th, right?
I'm going to confirm that, but I think you're right. But I'm going to confirm that. In fact, I might post an announcement about that as well. Okay, let me see here. Okay, so the next and final chapter, unfortunately, we can't get to. Well, that will be the final chapter actually. Is chapter 14, which is a relatively short chapter. So let me publish that now. All right. So that's chapter 14. Make sure you watch the videos for that chapter as well. So come prepared to discuss that chapter. And there's something else which escapes my mind right now that I need to tell you guys about. Oh God, I'm getting old. So I told you about the test. Oh, and I'm going to post an announcement about this as well. If you have not turned in any of the assignments that we have done in the past, for the past semester, I'm going to extend to you the opportunity of turning it in by Wednesday of next week. I'm going to post the announcement, right? After that, I will not be accepting any late assignments, all right? because I need to make sure that I grade everything in time so that I can meet the grade, the deadline for submission of grades, all right? So I'm going to make an announcement about that. Now, somebody's asking a question here. For the final exam, do we go to your class? Yeah, that's a good question. You know what? Because I've had some issues with, I'm sorry, for you guys who don't know what she's asking. A young lady is asking for the final exam, do we go to your class on May 6th or do we book at the testing center? I need to inquire about that because I remember in the past, they have had some issues with booking because the slots basically fill up very fast. So I'll look into that. If that's not the case, that means we'd have to come here in person to do the final. So I'll find out and inform you guys about that. Okay, somebody else is asking another question. Will you be able to post the Zoom recording? Yes, I will do so ASAP. And I think you're referring to today's class, right? And that is being asked by Brantley. So yes, I will do that. And somebody's asking for me to publish a PowerPoint. Okay, I keep forgetting to do that. So let me do that now. So the PowerPoint for today's class is chapter, oh, wait a minute, it's published already. Chapter 12. So yes, it's there already, all right? Also, I have received my test number 2 grade. So this is Negron. Okay, I'll have to look into that. In fact, tell you what, have you sent me an email already? Did we talk about this? If not, then send me an email indicating where you did the test and what date, because I need that to track it down if I have not graded it yet. All right? So send me a quick email indicating which testing center you did it and oh, you did send it? Okay, I'll have to look into it. Just send me another one. I don't know what's going on. When did you send that email? Let me ask you that. When did you send that email? Because if you sent it yesterday or the day before, I have not gone to it because I got a load of emails that I've been trying to reply to and they keep coming fast, which is usually the case at the end of the semester. But let me go back up here. Okay. So Miss De La Vega is saying there are very few slots on that day when I did check. Are you talking about the finals week? Okay. All right. I'll have to look into that. If anything, you guys would have to probably just come by my office during office hours. Okay, you send the email on April 20th. Okay, I'll have to look into that. But send me another email just to remind me. All right, and I'll look into it. Oh, by the way, Miss Negron, so did that email include your where you did the test? Okay, so do that. Send me an email indicating where you did the test and what date. Because I need that in order to track it down. All right. Okay, that's pretty much it for today, folks. So I'll see you guys next week.
Mr. Nicely.
Oh, yes, sir.
All right, can I do test 2 with you? I've had issue with getting test 2 done. Can I do test 2 with you, or would I have to schedule it? I think I can still find time to schedule it.
Okay, yes, you can do it with me. You'd have to come by my office hours. Like, for example, today, I'll be in my office. I'll be in my office today from 2 to 5.
All right, if I can't get it done today, could I still get it done Monday?
Okay, Monday, I'll be in my office from 2 to 5. Yes, so yes,
all right.
Monday is possible, yeah.
Thank you. Also, with my test 1, I realized you graded test 1. You send it in an email, but it doesn't appear on Canvas. So like you graded it, I can see the grade, but it's just not on Canvas.
So you're saying that I graded your test and put a grade on it, but it's not in the Canvas shell?
Yeah, the grade doesn't appear in Canvas.
Okay, I'll have to look into it. And again, send me a quick email just to remind me, because you telling me this, I'll forget. So send me a quick email describing the situation, I'll look into it.
All right. Thank you.
Okay, oh, somebody's asking for me to publish some chapter 14 PowerPoint. Okay, let me do that now. Okay, so chapter 14 PowerPoint is now published, so you guys can have access to it. All right. That's it for today, folks. So I'll see you guys next week.
Professor Pete Nicely, I have a question.
Yes, ma'am. Oh, somebody, oh, hold on 1 minute. Let me check. Somebody has a question in, oh, somebody was saying, thank you. Okay. Yes, what's your question?
So for test 3, would we take it next week?
Yeah, any day next week from Monday through Friday.
And I was trying to make an appointment with the testing center, and the only availability that it showed up was Wednesday at 8:30 a.m. And I'm not able to make that time since I do have a class on Wednesday. So I don't know if there's any other way we could take the test. Because
Okay.
I checked for the whole week and there was no availability but Wednesday at 8:30 a.m.
All right. Let me, and this is where, the Ocala campus?
Excuse me?
Is it the testing center at the Ocala campus?
Yes.
Oh, okay. Let me, all right, tell you what, if that's the case, then see if you can come by my office during my office hours. And you can do the
Okay.
test at that time.
Okay, I'll try because I have a pretty busy week. So if not, I'll just email you to try to
All right.
schedule it for a different time.
All right, no problem.
Okay, thank you.
Yeah, all right. Okay, so for you guys out there in Zoom, I am going to sign off now.
Oh,